Hi Kidlets, this is your notes video on sunspots. We can see on just this title slide here that sunspots appear as these dark spots on the sun. So we're going to look at why that is, and remember you have that homework assignment where you are having to track these spots. And we can see all of these different regions from a cluster of spots to lighter areas to what looks like single spots. So sunspots are areas that appear dark next to the brighter sun because they are areas that are significantly cooler. So whereas the majority of the sun is about 5,800 degrees Kelvin, sunspots are about 1,600 degrees cooler than that. But even though they appear very dark, these would still be brighter than the moon. So it's all relative just because the area surrounding it is much brighter. Now the reason that these are much cooler is because there are concentrations of magnetic field flux which inhibit the convection below. And remember, convection is the rising and sinking of heat from the hot core, which then migrates photons out through the radiative zone. Sunspots have some relatively predictable behavior. We can see that in this picture here we have a pair of sunspots, and I'm not talking about this one and this one, I'm talking about these two. So these two most likely have opposite polarities, and one of them is going to be opposite of this one as well. So they generally form in pairs, and they form at higher latitudes, so about 30 degrees above and below the equator. And throughout their lifespan of approximately a month, they would migrate then towards the equator. They can get larger and smaller within the same cycle and can even get larger again. So as we'll see in the upcoming slides, because each of these spots have an opposite polarity, as they migrate, one will be drawn more towards the pole and the other will be drawn more towards the equator based on that polarity. So sunspots can expand and contract as they move across the sun's surface, and these can travel at a rate of up to 160,000 kilometers. And large ones can actually be visible from Earth without the aid of a telescope with the naked eye. Sunspots are really important to the prediction of space weather because these have been known to accompany secondary phenomena such as coronal loops, solar prominences, and then reconnection events between areas of opposite polarity, and also solar flares. So CMEs, coronal mass ejections, tend to originate in these active regions that surround visible sunspot groupings. We can see these in other stars too, but obviously we wouldn't call them sunspots, we would call them star spots. But we know that this is a phenomenon that happens in all stellar bodies. We would call these dark areas similar to what we would call an eclipse in terms of shadow. So we would have the darkest region, which would be our umbra, and this is where we have the most intense magnetic field activity. And here the magnetic field lines would be vertical to the surface. And then we have the lighter areas, which just like in terms of eclipses, we would call the penumbra. And here you would start to see some elongating of the magnetic field lines that would no longer be vertical to the surface. So here we can see some solar activity extending up from the spot. So we've got a single spot. We can see some of this granulation here. We can see some brighter spots, and we can see these flare events, and we can actually see some connected loops, which would be prominences. This solar activity is directly related to the magnetism within the sun. So just like we can observe a bar magnet and we can observe those magnetic field lines based on the pattern of magnetism, we can think about the sun as being the same way. So we would have a magnetic north, we would have a magnetic south. But as we'll see, because this is a rotating ball of gas and plasma, as it's rotating and the sunspots are indications of magnetic activity that has reached the surface, that rapid rotation of this gaseous body causes these magnetic field lines to become really complicated. So we see times of repeated reversals of polarity within the sun. So solar cycles and sunspots have been recorded since approximately 1750. These are very easy to observe. You guys will be doing this in class. But we have now a couple hundred years of relatively accurate sunspot recordings that have been recorded from astronomers all over the world. They all correlate together. And we can see this pattern emerge of sunspot behavior through time. And this is all due to the changing structure of magnetism within the sun. So in the sun and all rotating bodies, because they are spherical, we see areas around the equator that rotate faster than areas at the poles. We see this in Jupiter, where you have a couple hour difference between the rotation at the equatorial region and rotation at the poles. So on Jupiter, it's a difference of about 10 hours at the equator and about 12 at the poles, but on the sun, we have a difference of about 25 days at the equatorial region and 35 days at the poles. So anywhere between 25 and 27 in that equatorial region. So we call that differential rotation. This also happens on Earth. Even though Earth is not gaseous or plasma, it is rocky, because it is spherical, we have a slightly faster rotation at the equatorial region. And this has consequences for rocket launches. So launches are always done at the lowest latitude politically possible, because obviously politics play into where you can actually launch a rocket from. But there's a reason that U.S. launch sites are at Cape Canaveral, Vandenberg, and now Elon Musk with SpaceX is building one in Texas on the Gulf of Mexico. Because as you decrease your latitude and get closer to equatorial regions, you increase your delta V. You have a greater thrust because you can use the Earth's momentum and the Earth's rotation to be able to get some extra boost without extra propellant, which all equates to cost. So it is actually more expensive and requires a faster speed and a higher degree of thrust and specific impulse to launch from higher latitudes. Fun fact. So because of that differential rotation, we start to see sunspots that migrate and dissipate. Due to that differential rotation, we start to see some stretching and stressing on the sun's magnetic field. So we see those magnetic field lines begin to be stretched around the body, around the star, and this then causes these spots to move and to migrate and to dissipate. This can also cause intense solar storms. So we can see that these spots tend to form in pairs. We can look at this model of differential rotation. We can see that if we have spots that all begin at approximately the same longitude, the lower latitude spots are going to be pulled further due to that differential rotation. So in terms of pairs of sunspots, we have, remember, opposite polarities. So we would have one spot that would go towards the equator and the other spot that would split and migrate up towards magnetic north. And as this process happens, we begin to see these spots that migrate, they fragment, and they split. And this would be called the dissipation stage. So there are two ways to look at determining how long the sunspot cycle is. If we were to look at just one period of positive polarity or normal polarity, we could say that's approximately 11 years. But the time it takes for it to be normal polarity, to reverse, and then to be back to normal polarity would be 22. So because we have this complicated magnetic field that then becomes stretched and stressed throughout that cycle, and we have these effects of that on the surface, that causes these magnetic field lines to become very complicated. It causes them to twist. It causes them to become intertwined. So what we see on the sun is that over time, over approximately 11 years, the magnetism on the sun reverses. We actually see this in the Earth too, and we find evidence of that on the ocean floor. But we haven't figured out what the pattern is on Earth because it doesn't seem like there is a cyclical pattern. But because we have this record of sunspots since 1750, we can track their migration over time, and we can then determine what the magnetism would be at that time. So we can see that there are these peaks and troughs, and we have periods where they're higher and periods where they're lower. And we would call these sunspot minimum and sunspot maximum. So when we have solar max, there is a higher degree of sunspots, and this would indicate a warmer climate than on Earth. So this does have direct consequences for Earth's climate. Now, think about that, though, for a second, because sunspots are cooler regions of the sun. So if you have areas that are cooler, how could that possibly have an effect on making Earth warmer? And the answer to that is that when you have these regions of cooler areas, the areas surrounding them tend to be hotter. So overall, the overall intensity of the sun is actually greater during that time because of these surrounding areas. Those faculae, which tend to be the bright spots, they're warmer. Those areas then cause the flux of the sun to be a little bit higher, which then has a direct consequence to the temperature on Earth. And we can just see that pattern here from the 50s up to just past 2010. So one thing that is commonly cited by climate skeptics is blaming the solar cycle for the current period of warming we're in. We do see in the historical record that there is a correlation between solar activity and climate on Earth. However, this change is extremely small, and we do not see these patterns on the magnitude of the solar cycle. But there has been noted times of lower sunspot activity, which is correlated with a dip in temperature. The most significant is called the Maunder minimum. This was about a 50-year period, also called the Little Ice Age. So this time was recorded as a time of unusually cold weather in Europe and in North America. And this period of cold associated with this short period of decreased sunspot activity, the cold period, lasted until approximately 1850. And we can see this climograph here over on the side, which indicates that. So this then provides some of that evidence. So during that Little Ice Age, this was also when we had the potato famine, when you had a third of Europe die. So there was, a direct correlation there. So I've shown you a few of these different diagrams. We call these the butterfly diagram for obvious reasons, because this actually does look like a butterfly. But if you stop and think about what it's actually correlating. So we have time on our x-axis and we have latitude on our y-axis. So this is actually a map over time. So we can see that each of these little pixelated dots is a sunspot, and it's tracking its migration, its dissipation, and new spot formation over time. So we could see how during this period you had spots that started higher, migrated lower, new spots that started higher, migrated lower. So over time, when we correlate that above and below the equator, that looks like a butterfly. So we can see some increase in solar activity here towards the 2000s, and we can see that decrease here, which was correlated with that Little Ice Age. So as I said before, when we have a new solar cycle that begins, that would be a time of reversed magnetic field orientation or reversed polarity. And that's due to these magnetic field lines that become so convoluted, twisted, stretched, and stressed during that time. And that's a correlation between these opposite polarity sunspots. So those spots are moving. Their magnetism that is attached to the interior structure of the sun then interferes with the overall magnetic field of the sun, and it becomes so complicated that the poles actually switch. And we see this, we have tracked this throughout the last couple hundred years of looking at sunspots. But this actually, the spots on the surface serve to rearrange the magnetic structure of the sun. So lastly, I wanted to touch upon some of the solar effects of sunspots. So we have two different ways that we can see the effects of sunspots on the surface. We have flares and we have prominences. And prominences are connecting areas of opposite polarity. And prominences are really common. So this would be like a magnetic reconnection. These happen a lot more commonly than flares do, and these can rise up about 150,000 kilometers off of the sun's surface. So here we can see a couple different reconnection events. We can see this one extending far into the chromosphere. But then we have flares. And flares are the most violent type of solar activity. These would be when you have a sudden brightening above a very large sunspot grouping between these areas of magnetic reconnection, and you have an outburst of charged particles or cosmic rays. So these can increase in high energy radiation, and these can be correlated as well to CMEs, coronal mass ejections, and coronal loops that we see when viewing the corona. And here we can see in this picture, in the visible portion of the spectrum, we can see one of those outbursts here, which would be one of these prominences that then it had such intense magnetic activity that it caused an outburst of those solar particles. And as we'll see in the next section, these can definitely have effects on Earth in terms of interfering with many different systems that we rely upon. So that is the last of your notes. I will see you in class.